So in this part, we are going to rearrange our project a little bit and start optimizing our scripts. So currently, we have our all neighbor script and everything's working perfectly fine as it should be. And for now, let's load our 3x3 grid, and it is going to give us some 8,000 solutions. And it is not giving 8,000 solutions because at the start um, we were checking only 8,000 solutions, and what we need to do is let's remove this equal to j less than instance dot level size. It is going to create all the solutions. Now let's go inside Unity and let's see, it is going to show us 8,000 solutions. So not 8,000, they are almost 9,000. So these are the solutions that is showing up. And if we have it turn it pretty fast and have it show only the results, you'll be able to see like most of the solutions are just color changes and the direction changes. So the true solutions are only three depending on how you define them. So if we just change the direction for any of the solutions, then both of them are pretty much similar. And if we switch between colors, then also they are same. Now let's create our two scripts that we are going to use, which is the optimize neighbors and our vector to point. So it is another script that is going to be after we have optimized our current script. So vector to point, and let's open up the Visual Studio. So first we are going to rearrange all of our scripts. So we need to attach namespaces, and we'll start creating namespaces for our level generator. So level generator scripts, and we are going to add a namespace to our level generator. So Control K and Control S, and we'll call this connect dot generator. And after for node renderer, similarly it is going to similarly inside our connect dot generator. So Control K, Control S, namespace, and it is going to be connect dot generator. And after that we have our random spawning. So let's assign a namespace, and we'll add connect dot generator, but we are going to add random spawning. And similarly for our all neighbors, so it has two classes, connect dot generator, and again we'll add all neighbors. So added. Now let's add namespace for our optimized neighbors. Control K, Control S, namespace, connect dot generator dot optimized, and finally for our vector to point, connect dot generator dot vector to point. So I could have assigned some different names, but for now let's have as it is. Now what we are going to do is let's save a vector to point, and we are going to copy our grid data class and paste it inside our optimized neighbors. Both are going to use similar scripts. And whatever we have inside our all neighbors class, we are also going to copy that. So everything is arranged perfectly fine, and similarly So this is our so there are not any errors, and everything is copied perfectly, and we don't need to do anything. Now what we need to check is if everything is perfectly copied and the script is working fine. So we'll close every other script, and then we'll go inside Unity, and we'll remove our all neighbor script, and we'll add our optimize neighbor script, which is going to have all the references attached. And speed multiplier, let's set it to 1000, and everything else is going to be similar, and we'll hit play, and it will show us error because our optimize neighbors does not implement the generate method interface. So it will try to get the component, but it will not get it, and that will return null. So let's go inside Unity and let's hit play, and again it should show us our 9000 solutions. After we have done that, we are going to go to the coding part, and I already recorded this section almost 3 times, and most of the times there were errors, so I don't know why did that error happen. And everything was perfectly fine with the code, so I'm just going to use the naming conventions and everything else what I have created before. So for our optimized neighbors in our grid data class, we need a function to get all of the similar grids. And what grid types are similar? So any of the 4 rotations for a grid are similar, and if you flip and rotate it again 4 times, so they are similar. So 4 plus 4 is 8, so they are going to be similar. And I'm going to create from the starting method, which is going to return a list of grid datas, and we'll call it get similar. And we don't need to pass any parameters, but we'll need to return a list of grid data. And let's call this result, and it is going to be a new list, and grid data add data, and for int I is equals to 0, I less than 4, I plus plus, we are going to create new add data with our current grid, which is going to current post.x, current post.y, and we'll pass the color ID, and for the reference we are going to pass this, and we'll use result dot add data, and again we'll copy and paste it again. Now before that we need to apply some rotation, so for this we'll pass a rotate, and we'll pass I, and for our next grid we are going to call the flip function, and again we'll pass I. So it is going to need two public functions to rotate and flip, public void rotate, and it is going to take an integer, and also a public void flip, which is again going to take an integer. So what our rotate function is going to do is just call the rotate function, and we'll need to create our rotate function. And inside our rotate function, it is going to change the values for our positions. So let's create a dictionary which goes from v to int to an integer, and let's call this result, and it is going to be a new dictionary. And for int I is equals to 0, I less than level size, we'll need to create our level size. So level size is stored inside our grid data, and it is going to be a static integer. Mhm. And at the start, when our grid data is created, we'll set our level size to be equal to level size. And here at the end, we are going to return the result. So let's see how our rotate function is going to work. So for int j is equals to 0, j less than level size, we'll set the result is equals to grid, and for here we are going to call our rotate function, but we are going to pass a new vector to int, and we'll pass the ing, and we'll need to create this function, and again we'll create a new vector to int, and here we'll pass the ing. And after all of that is done, we have stored the values in a new dictionary. We'll need to reassign our dictionary. So grid for our new vector to int of I comma j should be equal to result new vector to int of I comma j. And after that, we also need to rotate our current position, and we'll need to first create a function to rotate. So private vector to int, and we'll call this rotate, and it needs to take our value for position, and we'll create a result which should be equal to position, and our result dot x is going to be pose negative position dot y, and result dot y is going to be equal to position dot x, and we need to subtract it by level size -1, and we'll return the result. So everything's yeah, so that's how rotation is going to work. It is going to rotate the each point, store it in a new dictionary, and reassign the values inside the grid. And the rotate function is going to work individually for individual points. Now, similarly, when our flip is called, we are going to rotate it depending on the count, and we are going to flip it. So let's create a vector to int, and we'll call this first pose and second pose, and again we'll use a for loop, and here we need to have level size divided by 2, and one more for loop where it is going to be level size. And let's first get our first position, which should be equal to ing, and after that our temporary color is going to be grid for our first position, and our second position is going to be flip of our first position. And now we'll need to create our flip function, which is again going to take a position, and what it will do is it will return a position, but before that the position's x coordinate is going to be negative x coordinate, and we'll add level size -1, so it works perfectly fine. And yeah, and instead of void it needs to return a vector to int. So we have the first position and the second position, and our grid for the first position is going to be equal to grid for the second position, and our grid for the first position. Second position is going to be equal to our temporary color, and that's how our flip function is going to work. So as you can see, we rotated and flipped, and we created a new list which returns all of the similar grids. So it is going to include the grid itself and its four rotations, and the flipped grid and its four rotations. And whenever we want to check for similarity, we are going to compare it with this list. And let's go inside Visual Studio and let's see if there are any errors. So currently we didn't do anything. The only error that should happen if we have any console error. So it is again showing 8,000 solutions. And in the next part, we are going to explore our linked list data structure. So you you can directly call it as linked list, as it just takes the value, and the only function that we need inside this linked list is adding and inserting. So and we are not going to go backwards, so our linked list is going to have reference to first and the previous and the next, but in this we are going to have a reference to the next. And uh, before the insert function, which was a little bit time consuming, so whenever insert works is if we are inserting the 0th position, then it will move everything towards the right. So the copying takes time, so that's why we are going to use linked list. And whenever we add a new value, which is a new grid data, we are also going to create a set which is going to check if the value is already present. And whenever we add a value, we are going to add all of the 8 similar rotations and reflections. So we are just checking only one of them. So it is also pretty useful because after some iterations there will be similar grids, and we don't want those solutions to be working. So at the start, as you can see, only three of the positions for the 3x3 grid are same. So the corner, the center corner, and the center. Everything else is similar. So similar things will happen when we increase the grid's flow. So that's what we are going to do in the next part. So we'll create a linked list and we'll see how we'll use it. So in the previous part, we created a list to add our rotations and reflections, and we are going to create our linked list in this part. So our linked list is just going to be a simple data structure. So in our default list, whenever we want to add or delete, it takes a little bit of time, and whenever we want to create a new size, new grid, new element into the list, if there is not empty space, then it is going to resize it. But most of it is not happening inside our linked list, as the working is pretty simple. So yeah, let's create our linked list first, and then we are going to see how it is going to be used. And after that, we are also going to create an hash set comparer, which is going to be whenever we want to create a set. So our linked list is going to be a class, and we are going to call this grid list. And inside our grid list, we are going to have a public reference of grid list, and we'll call this next, and a public grid data, which is going to just call data. And for the constructor, we are just going to pass our grid data, and For the next, we'll set it to null, and we also don't need this. So this is going to be our simple linked list, and whenever we want to go to the next index, we are just going to set the next. And if we want to delete something, then we'll delete that. And we are not going to delete anything, but whenever we want to add anything in between, what we'll do is we'll add this to our current next, and we'll set whatever is added next to whatever previous added was. So if you have worked with data structures, and you'll see that it is almost how a linked list should work, but we are not having any previous and next. And before, at the start, instead of our list, we are going to use our grid list. And I already updated the repo inside the GitHub because there were some errors, and we will use the previous commit that we have done to solve it. So as you can see, it is showing a lot of red marks, which are the checking grid that we have used, and we'll start uh, updating it. So we have a list of checking grid, and again we are going to have an hash set, which is going to be for the grid list, and we'll call this grid set. And we need to set our grid set in the start. So our instance we have added our grid set is going to be new hash set, and our checking grid count is going to be 0, and we'll need to create the checking grid count. So private long checking grid count. So whenever we want to modify or check, we are going to create a new list, and we'll modify that. So let's see how our start method is going to work. So we'll create a new grid data, and let's call this temp grid, and it is going to be new grid data, and we are going to grid data for the 0, 0. And for now it's going to be a duplicate. Let's create a grid list, and we'll call this temp list, and it's going to be a new grid list for our temp grid. And after that we'll set our checking grid to be equal to our temp list, and we'll add to the grid set, and we'll pass our temp list. So we'll need to create our add to grid set function. So it should be directly below add to grid set. It needs to pass a parameter grid list, and we'll call this grid list and add list. And what we are going to do is we'll create a grid list, temp list, and for each item in our add list dot data dot get similar, so it is going to return all of the similar items. And what we are going to do is we'll create a new list for each item. So temp list is going to be new grid list for item, and then we'll check if our grid set dot contains our temporary list. Then if it does not contain, then we'll add, and we'll increase our checking grid count. And that's what we are going to do for our rest of the script. So we'll create a grid, then we'll create a list is going to be new grid list of temp grid, and after that we'll check if it is contained. So if not, our grid set dot contains our template, then we'll add. But before that add, where do we need to add? We don't need to change our checking grid because we need to have a reference to that. So we'll create a new list, and here we'll call this a add list, and it is going to start at checking grid. So add list dot next. So at start there is only going to be one list, and next will be null, and we'll set add list to be add list dot next, and we'll add to our grid set our temporary list. So it will add everything, and after that uh, inside our showing start coroutine, uh, let's comment this out first and how we are going to show. So let's create a new list, and we'll call the show list, and it is going to show our checking grid, and at the start we'll check if our show list dot next is equals to null, then we'll return, which is going to be yield break. And instead of s complete, we'll check if our show list dot data dot is grid complete, then we'll increase the count. We don't need to increase the count here. And let's delete. So our show list is going to be show list dot next, and before that we'll check if our show list dot next is equals to null, then we'll yield break. And instead of render grid, let's pass the show list dot data, and here we'll pass the checking grid count, and the timer has increased, and the show list is going to be show list dot next, and we don't need to check it again because do we need to check it again? Hmm, hmm, hmm. Mm, 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 mm. So if next is equals to null, then we'll break. So we checked our current list and there does not exist any next list, then we are going to break. Okay, so it is fine. And after we have done that, next should not be null, there should be a next. So yeah, it should be fine. So show list is going to be show list dot next, then it will go through this whole loop again. So for now looks like this should not show up any errors, and let's see if it is showing us any errors. And as you can see, there are so many. Yeah, so system.security doesn't matter. So for now let's see if our current list is working perfectly fine. And mostly we changed all of that inside the code, and if it crashes again, then I'll need to set everything up. So there are only 10 of them, and we only showed 1 2 3 4 5 6 7 8. The next was null. So let's go inside Visual Studio and let's see why it happened. So if our show list next is equals to null, then we'll break. We don't need to do that at the start. We are going to do it at the and not next. Let's use show list is equals to null, then it should break. And if show list is equals to null, here we need to check if next is null. Okay, so now it should show us all 9 of our grids, and to have it show clearly, let's add simulate. So as you can see, it showed all 10 of our grids. Now let's see how we are going to work with our solve paths. So let's uncomment everything, and let's see where all of the errors are. So let's have it not divide by speed, and we are going to approach different method here. So while we can solve it is modifying the checking grid, but the condition is going to be different. So iteration per frame and current iteration. So let's create a grid list and we'll call this solve list, and it is going to start from checking grid. And let's also grid list for our connect list, and uh, a result grid list that we are going to use for each iteration, and our grid data for item. Mm, mm. And after that, we are going to have a grid data for our temporary grid and a grid list for our temporary list and our connect list. So I'm initializing the variables before, so it doesn't show any error. And let's create a V2 end for our checking direction. And while we can solve, first we'll initialize our result grid list, and it is going to be our solve list. So we already set the solve list at start, and after that we'll check if our solve list is equals to null, then we are going to set the can solve to false, and we'll use yield break. Else we are going to solve everything. And let's first get the item. So it is going to be result grid list dot data, and for each direction, yeah, so we are going to copy everything here. So let's delete that. So for each direction, we are going to get the checking direction, and instead of checking grid dot insert, let's remove everything. That is item dot solved is going to be true, current iteration plus plus, and yeah. Hmm, hmm, hmm. At the end, everything is done. what we are going to do is we'll set our sol list to be sol list.next, and if our current iteration is 0, we'll wait for null 1 frame, and here we'll pass time dot delta time, and current iteration plus plus, it is going to be checked somewhere. So let's see how we are going to add. So let's first create a temporary grid, and it is going to be new grid data, and here we are going to pass our checking direction dot x, checking direction dot y, and item dot color id, and our item. So it is going to create a new copy for the direction, and after we have created a copy, we are going to temporary list. So new grid list of our temporary grid, and then we'll check if our grid set dot contains our temporary list. If it does not contain, then we'll add to our grid set our temporary list. And we are going to modify our current list, which is going to be our result grid list. So we'll first get the next, then we'll set the result grid list next to the temporary list, temporary list next to be equal to our connect list, and finally we'll set our result grid list to be equal to result grid list dot next. So it is going to work similarly, and we are going to pass similar values here. So here we'll add +1, and everything else is going to be similar. So it is going to solve all 8,000 of the solutions. So for now there are not any major errors. So let's see if our linked list is working fine and we implemented it correctly. So let's hit play, and let's suppose it does not have a show here. So total number of solutions were around 8,000, and as you can see it showed us 10,000 solutions. So maybe it checked for 10,000, and yeah. So we added a zeroth grid at the start, so it increased by 1/9. So that is some issue. And it did not check for equality because our 0 0 when we added it start, and our 0 0 when we added it next, it is just going to compare the references. So that's why we have 10,000 solutions. And everything's working perfectly fine. So let's hit play and let's see if it gives us 10,000 solutions again. So as you can see, there are almost 10,000 of the solutions, and that was this part. We instead of list, we used a grid list. So there is much less time for our insert and add operations to take place. So managing a list is almost pretty much hard. So whenever you delete and insert, it takes off and time, and a linked list just does it in O of 1. And let's see how we are going to compare our two grids in the next part. So in the previous part, we applied the linked lists, and we added all the grids into the linked list, as it was pretty fast. We don't need to get the index and move around much. So that's what a linked list is used for. And in this part, we are going to implement our comparison for the set. So as you can see, if we hit play, everything is working perfectly fine. We already created our set, but there are still 10,000 solutions. So now what we need to do is tell our set how it is going to compare. So we need to create a new class. So let's go inside Visual Studio, and the class we are going to create is going to be called grid set comparer, and it is going to inherit from so it is going to implement the iQuality comparer interface, and here we are going to pass the type, so what it needs to compare, so grid list. And if we implement the interface, it should create us two functions. So the first function is going to check if two grid lists are equal. So for now, let's return true, and let's return object.get hash code. So what conditions are going to be passed if two of our objects are equal? So if we have any other type like a vector2, it is going to check if both its x and y position are equal. But here we have a grid, and in our grid we have all the different position marked as numbers, and we'll need to check all of those positions. So let's first create a grid. So let's create a dictionary for v2 and to end, which are going to be our two grids, and we'll call them first grid and our second grid. And we'll get our first grid from x.data.grid, and then our second grid from y.data.grid. And after that, we are going to create a dictionary which goes from integer to integer, and this is going to be for our swapping our colors. So our two grids are going to be equal if both of them contain same colors. And so if the colors are same, then the color swap is going to correspond to 1122, and that's how the dictionary is going to be. But if the color swaps are not same, so that's where we are going to get duplicates. So suppose our first color was integer 0, and our second color was integer 1. Then if both of them are swapped, so if 0 is 1 and 1 is 0, then also our grid is going to same, just the colors are swapped. So that's why we need to create a dictionary. Then we'll check if our first grid, whatever color was that, it is swapped to some different color, then for the same color in the same grid, it should be swapped to the same color which was swapped first. And if the colors are different, that means both of them are different. So we are going to do that, and we are going to do for the post keys dot length. And first we'll set up our positions, and after that we'll first check if our first grid at position is equals to -1, or our second grid at position is equals to -1. So, and we'll check if it is not empty. So if it is already empty, then we don't need to check that. It will just save us two more checks, and we'll set is empty to be true. And after that, the first failure condition is going to be first grid at position is equals to -1, and at second grid at position is not equal to -1. So if one is empty and one is not, then we return false. And after that, there is going to be one more condition, and we are going to use OR. So what is going to be other condition? So if our first grid at position is not equal to -1, and our second grid at position is equals to -1, so that means at least one of them was different. So that's when it is going to return false. And after that, if our color swap dot contains key for our first grid of position, so if it does not contain, then we need to set. So color swap for first grid of position is going to be, so what it needs to be swapped with, it needs to be swapped with the second grid. Else, if it contains the key, then if our color swap for our first gridded position, so whatever color is there, the swapped color, which it should correspond to the second grid's color. And if both are equal, then it doesn't matter. But if any of them is different, then we are going to return false. And that's our equality condition is going to check. And after everything is finished, then we are going to check if our grid is empty and our positions are different. So x dot data dot current position is not equal to y dot data dot current position, then we are going to return false. So that's our equality condition is going to check, and at the end we are going to return true. So what would happen when everything is true? That means no two positions were different here. So if one is empty, different by empty and filled, so either both of them were empty or both of them were filled. And if would had been empty, then the color swap would have been set to -1. So if it is -1, then it will be converted to -1. So all of the empty positions, this is going to equal. So this would return -1 and this would return -1, so it will not turn false. And if there is some color that has been switched, so if the indexing was different, so if 0 has been switched to any other number 2, then whatever value that was as 0, it would have been swapped to 2, or else this condition would have been turned false and it would not have returned. So one color can only be swapped to just one color. There cannot be uh, same color swapped to two different colors, or else the flow would be different. And now we need to get it converted to hash code, and we are going to convert our hash code into a string. And for now we are going to start at empty string, and at the end we are going to return the hash code for that string. So let's create a vector to end for start pose and end pose, and let's call it check pose. I don't want to name it definitely. And after that we'll set our start pose to be equal to 0, and we are going to go to our level data, not level data, grid data dot level size, and again j for our grid data dot level size. So we are going to convert each of its neighboring positions to a boolean value, and start pose dot y is equals to j. So if it is empty, then we'll add 0 0 0 4 zeros to the string, but let's first check if it is not empty. Data dot grid, and we'll set the start pose, then it is not equal to -1. So if it is not equal to -1, then what we are going to do is for each where d in direction checks, we will need to add direction checks. We already had one direction check before, so I'll copy that and paste it inside our grid set comparer, and we'll make it static so it is not any different. So in our direction checks, we are going to get the check-in position. So it is going to equal to start position plus d, and after that we are going to check if object dot data dot is inside grid, And what should be inside grid is our checking position and our object dot data dot grid at our checking position should be equal to object dot data dot grid for our starting position. So that means there is an edge there, and if an edge exists, then we'll add 1. If it does not exist, then what we are going to do is add 0. And that was if it was not empty. If it was empty, then we are going to add 4 zeros. So it will return a unique hash code. And let's rearrange our up, left, down, and right. So that's how our grid set comparer is going to work. And if we have done everything correctly, then instead of having 9,000 solutions, not even 9,000, there are 10,000, we are going to have limited number of solutions. So let's see. Yeah, so we need to forgot one thing. So let's go inside Visual Studio. So we created this class, but we need to tell our newly created set that use this comparer to check both of them are equal. So we'll need to create a grid set comparer, and we'll call this set comparer, and it is going to be equal to a new, and we'll pass our grid set comparer, and we'll pass our set comparer here. So and also I forgot there was one more bug that I forgot. So that was our flip. We also need to set our current position to be flip. And yeah, so that was it, or else it may show some errors. Now let's go inside Unity and let's see if it is again showing up. Yeah, so as you can see, there are 316 solutions, and it almost worked pretty fine. And what we are going to do in the next part is mm, we are going to mostly do the profiling and see what is causing most number of issues. And now if we hit simulate, as you can see, there are only 3 solutions, and if we increase the time to 0.5, we should be able to see it. 0.2. Okay, so why did it not work? 0.01. There is some delay, and we need to fix that delay. So let's go inside Visual Studio and let's see where the delay is. So there is the first delay here. Generate paths doesn't need to have any delay. We need to initialize, and the coroutine is going to be started. And this is also fast. So let's have it. Return. So let's just pull it there. So this is going to show us our first, and there's some issue with our current delay here. So year return null. So the first frame was not already added, and our checking grid would have ended. So that was the first problem. And let's go inside Unity and let's see if everything's working perfectly fine. So let's decrease this to 100, and let's set it to 0.1, and let's hit play. Yeah, I got what would have happened. So our set would have finished. So as you can see, it is not instantaneous, but our show list would have ended. and let's set it to 0.2345, and after that, so as you can see, there are only three solutions, and let's set this to 10,000, and let's set this to 0.1, and let's see how this works for our 4 cross 4 grid. And as you can see, it solved our first grid, and after that it is taking too much time, so we'll need to decrease the speed. And mostly the speed, where is our speed? So okay, there is our speed multiplier, and I am not able to see if it is working perfectly fine. So it is slow for our 4 cross 4 grid. We didn't get a result, and our simulation almost got stuck. So if I didn't create the show result, I should be able to see it. So as you can see, till the second was passed, it just created only 3000 nodes, and it is pretty much slow, but we have reduced the total number of branches, or even this would have not worked. So in the next part, we are going to do the profiling, why this is only showing us so for our 3 cross 3 grid, we already found 300 solutions, and still it was pretty much slow, and we'll see how we can still decrease this. So it will get executed till it finds another solution, and I don't think it gets one more till it reaches 10,000 or so. So again, it is pretty much slow, and we'll do profiling in the next part. And it works for 3 cross 3 grid, so it should work for 4 cross 4 grid too, but we'll need to decrease the speed. Stuck on the profiling, and nothing has been cleared, so you are able to see that our most expensive method was with our dictionary. So let's clear it first. And what we are going to do in this part is wherever we used our dictionary, we are going to use a 2D grid, and we are going to reuse that grid everywhere. So to render our 2D grid, we'll first let's turn off optimized all random, and we are going to need the level generator. So we'll need to create a new method to render our grid, and it is going to take and 2D array. Hello. गया गैरेज ऐसा चल रहा. So we are going to need to create a new method to render our grid, and it is going to be similar to our previous method. So let's copy that, and here instead of a dictionary, we are going to pass and two-dimensional grid, and hmm, okay, so we are going to pass two-dimensional grid, and instead of a direction, we are going to again have an array. So private point array, and let's call this neighbor points, and it is going to be new point, and we'll pass our up, down, left, and right. So these are going to be our points, and let's rearrange them. So up, left, down, and then right. And how we are going to render it is instead of using a for each loop, what we'll do is for int I is equals to 0, I less than level size, for int j is equals to 0, j less than level size, and node grid, and node grid, and we need to pass our current grid. So we'll create a new point of ij, and we are going to initialize it. Mm, 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 mm. And after initializing, we'll get the current color, and it is going to be grid of inj. And after getting our current color, we'll set the number of connected nodes to 0. And if our current color is not equal to -1, then we go into each of the directions. So for int p is equals to 0, p less than 4, instead of 4, let's call this neighbor points dot length. And we are going to have a node array. So node array, and we are going to pass our inj here. And for each of the points, let's create a temporary point, and that point is going to be new point of inj, and we are going to add neighbor points of p. And after that temporary point is created, if our temporary point dot is valid point, and we'll pass the level size, and after that it needs to be valid, and it needs to have a same color. So the grid at our temporary point dot x and temporary point dot y should be equal to our current color. Then we'll need to create our node array first. So it should be inside our start methods. Yeah, everything is expanded. So where is our dictionary? And we'll create a private, and it is going to be a node renderer, and we'll call this node array. And inside our awake, where we set our node grid, we'll set our node array to be a new node renderer, and we'll pass our level size. And spawn node dot init node grid dot add. So here we'll set the node array for inj to be equal to spawn node, and that should add our node array, so it should not create any more problems. And whenever we want to render it, so if it is similar, then node array dot inj dot set edge will pass the current color, and then we are going to pass our neighbor points of p. So that is going to be the direction, and we'll increase the number of connected nodes plus plus. And after all of this is finished, if number of connected nodes is less than or equal to 1, then we are going to show the point. So node array of inj dot set edge, and here we'll pass our current color, and we'll pass this 0. So it is going to show us the rendering, and the render grid method is going to use from vector to point. And let's change from our base data class first. So everything's perfect here. Public static list of point direction checks. So instead of list of point, let's add a new. And there are going to be so many problems, but we are going to fix it. And instead of dictionary, we are going to have public 2D int. So it is going to be a new int of level size, and grid for our A and B is equals to -1. Grid for our current pause dot x and our current pause dot y, and again we'll need to new int of our level size, and we'll need to copy it, and our grid for our current pause dot x and current pause dot y, it is going to be similar, and here we are going to pass our level size, and what is going to happen is grid for our a comma b a a a b b b. So our grid at a comma b is going to be equal to grid copy dot grid at a and b. So it is going to copy the whole grid, and instead of is inside grid, we are going to pass our pose dot is point valid, and we are going to pass our level size, and item dot value, instead of item dot value we'll set the item, and here similarly we'll set the item, so grid complete, and item in grid is not neighbor, item is equals to color id, and we'll need to check for not neighbor, so we'll need to update that. So what we are going to do is for int I is equals to 0, I less than level size, for int j is equals to 0, j less than level size, and if grid at I and j is equals to our color id, and am I recording? Yeah. So it is equal to color id, and our new point of I and j is not equal to current position, then for each, for int p is equals to 0, p less than direction checks dot length, and we'll check if the past position minus our new point of I and j if is equals to our direction checks of p, then return false. That means it is a neighbor, or else it is going to return true. So there are multiple different loops, but in all it is going to return the same. And empty position, then it is going to, yeah, so we'll need to change this again. And it is returning a list of empty positions, so let's create a for loop and level size, for loop and level size. And if our grid at I and j, not I and j, a and b is equals to -1, then we are going to add new point for a and b. So there will be so much bugs to fix, but all in all it's going to be pretty easy. For each item in grid, if item is equals to color id, then result plus plus. And yeah, so we are going to do some optimization here. So our rotate is going to be called only once. So public void rotate. Add data, flip data, add data, flip data. So here we'll pass the add data, and also add data, and finally at the end it is going to be add data. And flipping is not going to call the rotate, we are just directly going to flip it. And temp color is going to grid at first pose.x and first pose.y. And similarly we are going to just pass the values here, dot x and second pose dot y. So as you can see, flip is working perfectly fine. And I don't think we'll need to pass any parameters in the flip, but there is only, yeah, there is one more flip. So let's remove the parameter and let's remove this, and we are going to add the result dot add data. And here it is going to pass the previous add data and set our current add data. Now let's see what our rotate is going to do. So rotate has a dictionary for point to integer of result, and again we are not going to use this method. So currently almost 1, 2 and 3 all of the errors are fixed for our current grid class. We just need to set up our rotate. So for int I is equals to 0, I less than level size I plus plus, and start is equals to 0, then int end is equals to level size -1 and while our start is less than and, then we'll set the temp to be grid of I comma start, and our grid of I comma start is going to grid of I comma end, and our grid of I comma end is going to be temp. We'll increase the start and increase the end. So what it is going to do is just flip everything across. So it is going to flip it, and if we transpose it, then it is going to return so int j is equals to I, j less than level size, So we don't need to transpose everything multiple times. It is automatically going to transpose it. Let's get the intent to be equal to grid of j and I and j, and our grid for our I and j is going to be equal to grid for our j and I, and grid for our j and I is going to equal to temp. So that's how it is going to work. So what is this first is going to do is it is just going to flip it. That's we have done it here. And for int I is equals to 0, I less than level size. So it is flipping rows. So I at the start, so whatever is at the first row position, everything is going to flip to the last row. And after everything is flipped, we are going to transpose it. So it is going to rotate everything by 90 degrees. And after that, yeah, already 19 minutes. So object dot data dot grid, we just need to pass everything correct. Dot x and dot pose dot y, and similarly dot x and y. First grid, and here we'll just get both of the grids, and hmm, 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 hmm. So this loop is going to be wrong. Let's use a for int I is equals to 0, I less than grid data dot level size. For int j is equals to 0, j less than grid data dot level size. And let's paste everything. And we'll need to change everything here again. So autocorrect is going to be pretty much helpful here. Dot x and pose dot y. And our pose keys is going to be, let's delete this. It is going to be new point of ij dot x and pause dot y dot x and pause dot y. Not color swap. So everything is yeah, it is good. And there is one more error where it is, so we are just going to pass the checking direction dot y. So we converted everything. Instead of dictionary, we are using a 2D array, and our render grid also should render everything correctly. Now let's go inside Unity, and first we need to see if it did show any of the errors. So currently it is not showing any errors. Our profiler is also working perfectly fine, and let's play. Okay, so outside I'll start is less than and grid of I and n. Hmm, 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 hmm. Yeah, that was because we are doing n plus plus, so that was one of the problem. So here we need to do start plus plus and end minus minus. Before it was n plus plus, so that's why it was showing error. So let's hit play. And as you can see, now it is working perfectly fine. And my profiler should load. So before it was slow, now mm, yeah. So as you can see, the overall it add to grid set, it just took 100 milliseconds. Previously it was in the range of thousands. And let's check frame by frame if there are any expensive frames. So most of the time it was we should be able to see it if we go inside our profiler and let's hit play, and we are going to go to our highest frame, which is showing up here 153. And this is taking a little bit more time. Grid set comparer, contains key, dictionary to generic equality. Okay, so our grid set comparer is also having some issues there. Hash set dot contains and hash set dot add. There is some problem with our dictionary. Yeah, grid set comparer get and set equals internal hash code is also taking 8 milliseconds, but it is doable. String operations are, as you can see, string.concat is the highest 5 milliseconds depending on the rest of the operations. And we need to see where we have a dictionary to. So let's go inside Visual Studio and let's check our grid set comparer. Okay, so this dictionary too is expensive. Dictionary2 dot contains key set item and get item. So should I change this instead of dictionary? Let's have it as an integer of array, and it is going to be new int of grid data dot level size. And how we are going to change it? So if not color swap, okay, so first we are going to check if not color swap of first grid at our pose.x and pose.y is equals to -1. Color swap for the first grid of pose.x and pose.y. So why is there an error? So if it is not equal to -1, then we are going to set it. And by default, we need to set it to -1. So let's do an for int I is equals to 0, I less than color swap dot count, color swap dot length, color swap of I is equals to -1. So it is going to swap each of the positions to something else, and if it does not match, then it is automatically going to return false. And let's see how that cleared our performance. So let's hit play, and outside the bounds of the array. So first grid at, so before checking, we need to check if first grid at pos.x and pos.y is not equal to -1, and so if it is -1, then this is going to get out of bounds array, and the maximum value is going to be the color ID, so it is not going to matter much. But if it is already equal to -1, then this whole loop will turn false. Else if first grid at pos.x and pos.y. So I'm doing this real time, that's why it is going to take a little bit of not equal to -1, then it is going to directly swap it. Maybe I should not add that condition here. Let's remove it. And nah, it was fine. So let's hit save, and now it should not show up any errors. So debugging real time is a little bit more. So as you can see, now it is fast. Let's go inside our profiler, and it should yeah, so it is fast, though we'll increase our speed a little bit. So let's set it to 32 and let's hit play, and again it is fast. So let's go our first call. So maximum time is 40 milliseconds, and rest of the times were slower. Now let's have it 1000, not 1000. Let's have it 64, and we'll hit play. So still our 64 is fast. We are going to increase the speed twice. And 128 is also working perfectly fine. So we are again going to increase the speed to 256. And now it is slowing down a little bit. So why is it slowing down? We are going to check. So add to grid set and hash set dot contains again most of the time, and there are almost 100,000 calls. Get internal hash code was 9 milliseconds, and self was different. Okay, and here it is again taking hash set dot add if not present, comparer, and hash set dot internal hash code. So as you can see, the rest of the time is for the string, so that's 45 milliseconds. So whenever it is getting an hash code, it is taking more time. Get internal hash code, and that's 45 milliseconds. And comparer point operations are taking 20 milliseconds, and garbage collection is also taking a little bit more time. And anything else? So there is also 76 milliseconds. So our grid set comparer is taking time as it is supposed to. So we decreased it by pretty much large margin. And let's stop playing. We'll clear our profiler. Instead of clear on play, let's hit clear and let's use a 5 and 2 and let's hit play and let's hit simulate. So we should be able to see how for individual frame how it is working out. Hmm. So this one is the highest. It has 1400 milliseconds, of which 1200 milliseconds is for. So most of the time is spent on hash set, and string.concat is taking almost a margin of the time. So here 18 milliseconds. And grid set comparer, there is also some garbage collection issue. So we'll need to reuse some of our points. Hmm, hmm, hmm. So let's go inside Visual Studio and let me compare our current set comparer to our previous comparer. So our get hash code is going to be revamped. The string methods are a little bit expensive. So grid set comparer equals, we already set this up, pause, first grid add pause.x, pause.y, and here we are just passing the integers, and this pose is always getting new, and maybe we don't need to set it to new. Let's just set the pose.x to y and pose.y to j. Most of the issues happening here, and the first grid we are passing it here, and we are just passing the integer x.data.current pose. We are getting the current position and we are checking, so it doesn't matter much. Now let's check into our profiler one more time, and then we are going to end this part. So it almost took a little bit longer than it was supposed to because we are debugging, and for the last some of the parts I created it myself on the go, so it was some of the optimization I did. So grid set comparer equals, again it is taking the highest amount of time. There is some garbage collection going on, and equals the self millisecond is 57. So why is this happening? Maximum amount of calls are inside the player loop. Let's go to the time and we should be able to see the percentage. So zero point 0.9 and zero point 0.3. So grid set comparer dot equals. Hmm, hmm, hmm. It got called 300,000 times. Don't know. So let's go inside our vector to point and let's check which was taking the highest amount of time. So this one took 43 and this one also. Hash set dot add if not present. So internal hash code is almost like 15%, and the grid set comparer dot equals, it is taking a little bit higher time, but there's nothing we can do about it. But what we can do about is getting the hash code. So our string builder is taking much more time because we are using a default string, and most of the time is spent on our grid set comparer dot equals, and it is not showing us what it is spending most of the time on. Maybe it is called multiple times, so that's why there is some issue. But so we'll see we'll optimize our script for our strings. So string is also taking 15% more time, so it will be optimized a little bit, and after that we'll see what we need to do. So in this part we are going to do the profiling, and we'll see why I took some of the steps in which instead of using a list I changed to a linked list, and also what further steps are we going to take. So we have our optimized neighbors. So let me go inside GitHub, and let me go to our breadth first search, cause that was our first script, and it will be reloaded, and you'll be able to see that now it is going to have the all neighbor script. So it is reloading scripts. So let's reload, and as you can see this is the previous version. I just changed the branch, and let's set the speed multiplier to be 100. So and for -1 let's simulate the code again. So as you can see there are 3000 solutions, and it is working perfectly fine, but as we go for our 4x4 grid, the number of solutions are increasing pretty fast, and even though we have set the speed to 100, it is getting slower and slower. So let's see what it is making slow. So what we are going to do is attach our profiler. So it should be control 7, and we are going to attach it to our game, and we'll turn deep profiling on. So by default it would be off, and we are going to turn on. So we have turned deep profiling on, and whenever we play the game the profiling is going to show us, so displaying live data. While recording to see the data, toggle live. Hmm. Hierarchy, main thread, CPU usage, memory. And if we hit simulate, and let's pause. So it should be paused. My PC is a little bit slower. So everything's paused right now, and as you can see, we are able to see our profile dot flush counter, not here. So we are going to see the highest step where it took much of the time, and we are not going to see for our editor step. We are going to check for our player loop. So it should be around here where it took the highest time, and let's see inside player it took the highest time. So scriptable script run delayed direct coroutine took the highest time. Then inside our coroutine the invoke move next, and inside our invoke move next the solve part took the highest time. And if we check inside our solve paths, the total all of the time which took the highest was the index of, and how many times did it get called. So if we open this again, index of and object equality comparer, this almost got called like how much is it, 1 to 26 million times, and it was almost, as you can see, it is pretty much too much big. And equality comparer is also, wait for signal, and Hmm. So that is the main issue here. So index of, that's why we stopped using the list. Instead, we used our mm, linked list. So that was the issue here. And nothing else is taking much time. Now we are going to go and check the same thing for our let's discard the changes. So it is going to discard all the changes and then it will be getting reloaded. So let's reload the scene. And we are going to switch to our caching branch, and it is going to reload our scene. So reload. And for our optimized neighbors, our 100 speed is going to be too much large. Let's just decrease it to 10 speed. So for our 3 cross 3 solution, before we had almost 10,000 solutions, and let's hit play. And now we are okay. So our profiler is getting ready and it is going to take a little bit of time. Hmm. So as you can see, if we hit pause and so 10,000 speed was pretty large. So if we go inside our profiler and we are going to check for our highest player. So everything okay, so everything just got removed. I don't know where it is. So I'll need to let's hit play. And what we are going to do is instead of 10,000, we'll just set this to 100. And then again, we are going to call play. And let's click on simulate and let's pause this. So now as you can see, it is going to show us all of our times. And so as you can see here, it took 317 milliseconds. Uh, we are not able to pinpoint it. So here it took 800 milliseconds. So we can check which step took the highest time. So there is our move next, and inside our move next, the highest time was for solve paths. And we open our solve paths. We are able to check our add to grid set and hash set dot contains. And in our hash set dot contains, the maximum number of time was our grid set comparer, and this inside our grid set comparer, the dictionary2 dot get item, which is the vector2 dot get int, it took the maximum amount of time, and it had almost like 100,000 calls, and that was just for this 90 millisecond. But if we go inside our optimized neighbors and we check this add and contains, then you should be able to see like the number of calls are going to get pretty high. So dot get item is, it has almost like 200,000 calls, and it took the highest time for almost 300 milliseconds. So our dictionary is not working fine with this data structure, and I just randomly used the dictionary at start. I didn't know that it will create such problems, or else I would just have used the arrays. So we are going to change it to arrays next, and not be able to see the next most difficult. I mean, the string methods also take too much space relative to that, so we'll need to use the string builder. So that is our optimized neighbors method. So we are going to add the script. So let's add our vector2 point, which is going to copy of our optimized neighbors. And what we are going to do in this part is our vector2 dictionary conversion was expensive. So we are going to create our own version of vector2 int, which is going to be a point, and we are going to apply that point. So our point, it is going to be in our main class, and main class, I mean, which is our level generator class, and our vector2 point. So reload. So we are going to go to Visual Studio, and let's see what changes we need to make. So our vector2 point is going to inherit from our generate method, implement the generate method interface, and we are going to need to copy everything from our optimized neighbors to our vector2 point, and also all of the classes. So they are going to have their own implementation. So let's copy these classes and let's paste inside our vector2 point. And also everything is inside our main class. We are also going to copy and paste it. So it is going to work similar to our optimized neighbor class, and everything else is going to be similar. Now we are going to check if it is working perfectly fine. So let's go to Unity, and we are going to add our counter, our grid count, and speed multiplier of 10, and speed of 0.02. And let's see if there are any errors. So if there are any errors, it is not going to work, and as you can see, it is working perfectly fine, and it is going to show us the 316 solutions. So everything's working perfectly fine, and if we pass our 0, then also it is going to create the solutions for our 4x4 grid. And also it is not pretty much efficient, but it works. We just reduce the total number of nodes it had to traverse. So for now it was checking for 9,000 nodes, and it was giving almost like 15 to 16 solutions, but now it is going to check only 300 nodes, and the total number of solutions unique for a 3x3 grid are only 3. So that's one point to note. Now let's go inside level generator, and let's go to our node rendering. So the first thing we'll need to do is we'll need to create a struct which is going to be public. So public struct, and it is going to be point, and it is going to have a public int of x and y, and a constructor public point, and here we are going to pass int x and int y, and what we'll do is this dot x is equals to x and this dot y is equals to y, and that is going to be our constructor. And then we are going to create a public bool is point valid. So what is going to check if a point is valid? So it needs to be inside the level size, and let's pass an int of max count, and we need to check if x is less than max count and y is less than max count, and x is greater than -1 and y is greater than -1. So if every of them is valid, then it is a valid point. and we are going to create a public static. We are going to add, so let's add a point, and we are going to need an operator, so operator, and this is going to be our plus operator. And how our plus is going to work is return new point, and here we'll pass p1 dot x plus p1 dot y, uh, p1 dot x plus p2 dot x, and p1 dot y plus p2 dot y. And similarly it is going to have a subtract operator, so let's copy this and let's use subtract, and here we are just going to change the sign. So these are the two operators, and after that we are going to need a public static point, and it is going to be up, and it is going to be new point of 10, and we are going to have similar points. So our vector2 int had up, left, so our left is 0, our up is going to be 0 and 1, left is going to be -1 and 0, and our down is going to be 0 and -1, and our right is going to be 1 and 0, and finally our 0 is going to be 0 and 0. So let's rename this. So this one is for 0, this one is for right, and this one is for down. So it is going to create all of those points, so whenever you want to use, so we are going to directly rename every v2 into point, so the type will be automatically changed, and it needs to have the all the operations which are valid for a vector2 int. Now we are going to create a public static bool operator, and this is going to be our equal to operator, and what it is going to return is p1 dot x is equals to p2 dot x, and p1 dot y is equals to p2 dot y. So both should be equal, and public static bool operator double equals y. Okay, so if we see, then it is going to tell us that we also need to implement not equal to operator. So let's copy this and let's paste it again, and here instead of equal to we also need a not equal to, and what we are going to do is if any of them is not equal, then we are going to turn false, and for equal both of them should be equal. So we have the equal and not equal operator. Next we are going to override public void public override, and we are going to override the equals, and to override that what we are going to do is let's create a point to be of type point of object, and what we are going to return is x is equals to a dot x and y is equals to a dot y, then both of them are going to be equal. And after that we are also going to override the hash code, so what we are going to return is 100 multiplied by x plus y and we are going to convert this to a hash code. So dot get hash code, and these are all the methods that are going to be needed. And let's convert all of our vector to into points. So we are going to do the edit and find and replace and files, and maybe, yeah, you'll not be able to see. So what we are going to do is current document, and we are going to find vector2 int and replace it with point. So find next. So as you can see, it is found all of our vector2 ints, and what we are going to do is replace all. So as you can see, it showed us 11 occurrences replaced. So previously it was point vector2 end, now it has been converted to point. Hmm, 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 hmm. And we also need to convert our node renderer. So let's do edit, find and replace and files, and we are going to convert vector to int, and it is going to replace all, so it will not show up any errors. So we replaced in the node renderer, we replaced in the level generator, cannot convert from. Okay, so the next we are going to replace is going to be inside our vector2 point, and yeah, so that is the only error that is remaining, and we are not going to change it for anything else as we already saved our project, so it is not going to show us any errors. Now let's create an edit, and again we are going to find and replace and files, and where is our vector2 int? So edit, find and replace and files. So there are going to so many, and we are going to do replace all, and as you can see, every occurrence where we added a vector2, it converted to an point. And let's see how our program works right now. Again, the dictionary is going to be pretty big, but maybe we have just decrease some of the load, so we are going to test it, and let's go inside Unity, and the parameters are going to be similar, so cannot convert. Okay, so there's a problem for our random spawning and also our optimized neighbors, so we'll also need to convert this. So let's add a vector to int, and what we are going to do is Control Shift H, and we are going to do replace all and save it. And also inside our optimized neighbors, let's get a vector to int, and we'll do Control Shift H, and we'll need to replace it, so I was just replacing everything, and plus replace all, so almost 50 occurrences were replaced, and we'll hit save, and now everything is changed to our point. And let's go inside Unity, and let's see if it is showing us different errors. So all neighbors. Okay, so there is one error, cannot convert. Pause index, item, color ID. So our all neighbors also need to be changed. So we are going to do Control Shift H. So Control Shift H and point replace all 25 occurrences are replaced, and let's hit save. And now we'll go inside Unity and we'll again check for errors. Are there any? So there aren't any. So everything is perfectly replaced, and now we are going to see if our current. So I don't know how much fast it is, but let's do the profiling. So let's go to Window, Analysis, Profiler, and deep profile is already turned on. So let's first clear, and we'll turn clear on play, and we are going to hit play, and we'll check if okay, so profiling is going to 190 and 1000. Let's see which is the most expensive method. So coroutine delete calls, invoke next method, solve paths, and vector to point of add to grid set, and again hash set dot contains is expensive. So get hash code, grid set comparer, get item. Again, it was dictionary to dot find entry. So object equality comparer. So we'll need to convert this dictionary to an yeah, we'll need to convert this dictionary to an array, cause still it is pretty expensive. But we almost had like low amount of method decrease time. So previously it was like around 300 to 400 milliseconds, but you won't be able to know depending on exact parameters. And similarly, our hash set dot contains is going to be large and add, and everything else is similar. So get similar is also taking much space, and most of them is just with the getter and the setter. So it is the most of the time it is taken by our dictionary. So we are going to convert that dictionary to a vector to int in the next part, and we'll do that. So we already checked where all of the most of the time was spent. So our garbage collection was pretty much higher, so it is 55 megabytes. And grid set comparer is having the maximum garbage collection. So for what it is spending that much time, I don't know. So that's almost allocated is 51 megabytes. And mostly I suppose it is for each of the points. So there are almost n square points, and each of the checks is going to be pretty much big. Time, garbage collection, allocation. Time in milliseconds, that is the most. Uh, mm, mm, mm. So hash set dot internal hash code is taking much time, and most of the time is spent because of the string concat and grid data dot is inside grid and whatnot. So we are going to optimize that, and our grid set comparer is only the most difficult one. So hash set dot add, add if not present, 21 and 13.4. 8.5 is for the string dot concat. So we should be able to decrease 8%. And similarly contains grid set comparer. It almost got called 1 million times. So let's clear this, and we are going to go inside Visual Studio, and we are going to see how our hash code is going to get. So here just we are getting the grid and we are creating a new int. So that's the only int that's created, and everything else is just getting and setting. So we just set the pose. We are also reusing the pose. So where it is creating much of the garbage collection. Grid set compare dot equals. This is static. So let's start with the get hash code. So we are not going to create a string. So let's create a 3D array and we'll call this graph, and it is going to be a new boolean of grid data dot level size, and cross 4, and start pose dot x and y, and for each this is going to be list of point. Okay, so let's get our direction checks. So instead of list of point, we are going to have it as an array of points. And we are going to change it here. Object.data.grid. So we are not going to need the if statement here. Um, mm, 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 mm. So instead of for each, we'll use a for loop. So if it is not equal to -1, we'll use a for loop, and here we'll pass the d, and for less than direction checks dot length, and direction checks as up, left, down, right. So we'll first get our check pose to be equal to our directions of t plus our start pose. And after that we'll set our graph for I, j, and d to be equal to this. So that was the previous value, or else what we are going to do is for int d is equals to 0, d less than 4, graph of ij d is going to be false. And after we have done that, we have converted to a boolean 3D. So we are going to convert into a 1D boolean array. So we'll call this result binary, and it is going to be convert 3D to 1D of graph. And so we'll need to create those methods. So we are going to create a public static, and it is going to return a one-dimensional boolean array, and we'll call this convert 3D to 1D, and we are going to pass a boolean three-dimensional array, and we'll call this array, and int L1 is going to be equal to array dot get length of 0, int L2, and int L3, and int L is going to be L1 multiplied by L2, and we'll multiply it by L3. So these are all the three lengths, and this is going to be our total size, and we'll create a result. So bool result is going to be new bool of length L, and what we are going to do is int index is equals to 0, and we'll use a for int I less than L1, for int j less than L2, and for int k less than L3. And we'll do result for our index plus plus is going to be equal to array of ij and k, and at the end we are going to return the result, and that should give us our convert 3D to 1D of graph. And after that we are going to convert this boolean to a long array, and it is going to be result long, and it is going to be called convert 1D to long, and again we are going to pass our result binary. Yeah, I'm recording. So public static, and here we are going to return a long array, and we'll call this convert 1D to long, and what we are going to pass is a boolean array, and let's get length is array dot length, and long count is going to be length divided by 64. So we need to length plus 63 divided by 64, and after that long result is going to be new long of long count, and for int I is equals to 0, I less than length, if array of I it is true, then we'll set result for I divided by 64 or equal to 1L, and we are going to do a left shift operation, and how many shifts we are going to do is I percentage of 64. So it is going to convert it to a long, and at the end we are going to return a result, and finally we are going to get a string, not a string, we are just going to return convert long array to string, and then we are going to pass our result long dot. So we'll need to create this method again. So again it's going to be public static, and it is going to take a long array, and let's hard return it empty string. And we'll use the get hash code. So we are going to use string builder here. So string builder, and sb is equals to new string builder, and for int I is equals to 0, I less than array dot length sb dot append, and what we are going to append here is sv dot toString. So string dot format, and we are going to pass new fixed. So we'll need to create a fixed length formatter. System.text, system.collections, and system.collections.generic. So I don't know how this fixed formatter works, but I got it online. And what it does, it converts yeah, so it should be here, and let me copy it. So this is our fixed length formatter, and we are going to use sv.append, and what we are going to pass is string.format, and the format we are going to use is new fixed length format provider, and the parameters we are going to pass is 20, and format is going to be 0 to D, and after that what we are going to pass is array of I dot toString. So that's how it's going to work, and it is going to give us our result, and I don't think there is nothing else to do. So I don't know how this iCustom format provider works, but argument dot is long and format, so 0 maybe stands for long, and I just searched for online, so it results in a more compact way of using strings. So previously we just directly added zeros and ones. It would have taken more memory, but what we did was converted to a long integer, and after that we converted that long array cause maybe the size may be higher, and we converted to a string, and our default string was using more memory, so we used a string builder. And now if there are not any errors showing up, everything should be working perfectly fine. So we'll hit play and we'll see if so as you can see, it is fast, pretty much faster than before it was. And let's increase the speed to 1000, and let's hit play, and again as you can see, it is fast. And if we increase the speed to 5000, then also okay, so it took a little bit more time, and now we should be able to see in our profiler why it took more time. So every frame is getting counted, and if I close the profiler, then it will be fast. Okay, so index out of range. It crashed somewhere. First grid. Color swap. Hmm, 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 hmm. So let's check for our -1, how much time is it taking, and we are going to clear our profiler first, and we'll hit play, and Hmm, hmm, hmm. So it again took 10,000 steps, and I don't know why did that happen. It should not have happened. There are going to be bugs. So let's first pause first and let's see what we'll need to optimize, and we'll also need to fix a lot of bugs. So most of the time was spent in hash set dot contains, 15% in grid set comparer. Mm, 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 mm. So it would have return false here. There is some issue going on here, amp. So we'll do the debugging in the next part. So we almost created, almost fixed everything. Let's see what we need to do. So the code is working speed. Uh, so it has sped up more, but there are also bugs. So there were some bugs last time we created our script. So we'll fix those bugs, and also there were some issues with our not issues. Our string builder was pretty much expensive, so I just found out a good solution. And the previous method for the search, I think I searched from Geeks for Geeks, and there was the long to character converter. And after that, I used chat gpt to create a new method which is which directly converts our boolean to an array of bytes, and there's some function which directly converts it to a string. So that was that. And for now our game is working perfectly fine, but let's attach our profiler and we are going to see which are the most expensive functions, and we'll try to minimize that. So this is our current game, and what we are going to do is run our game. So inside our level generator, at start we were just using a speed of 10. Now we can use a speed of 2.5 thousand, and we'll press simulate, and as you can see it is loading all the nodes. And we are going to go inside our profiler, and we are going to go to our most expensive frame, which is our this one. It is taking 900 milliseconds, which is almost a second. It is still not too much expensive, but we are going to see what is taking most of the time. So most of the time is taken by our solve paths, and inside our solve paths our hash set dot contains is taking 9% time. And grid set dot comparer, as you can see, we needed to fix this dictionary, so we are going to do that. I already did it before, but there were some issues, so we used an array, but there was a single condition missing, so that why it was not working perfectly well. And inside our internal hash code, so the main is our this, so the most we will be able to save is 5%, and inside our vector to point, both of them are going to have some like 5% or 5%. So get internal hash code, here it is taking 28% time, and the best we would be able to save is 20 to 30%, so we would not be able to see any more changes. But what would happen is, instead of running our code at speed of 2500, we should be able to run our code at speed of lower. So let's first fix our color swap. So our color swap was a dictionary. So as you can see, it is taking almost 3 to 4% of space, and we are going to convert to an array. And the array size, in the previous part we were making it level size, but it was not level size, so we need to have the color ID, and our color ID starts from 0 and the maximum is going to be the color ID. So it is going to be from 0 plus so 1 and color ID plus 1. And before checking, we are going to create bool can check is going to be first grid, and our pose.x and pose.y is not equal to -1. So this is the condition, and instead of using our contains key, what we are going to use is we will check if it is equal to -1. So we are going to set it up as -1 at start, and we need to see if we can check. And else if we can check, then only we can go, we are going to do the next part. And what we need to do now is set up our color swap. So I less than color swap dot length, and we are going to do color swap of I is going to be equal to -1. So by default at start it is going to be -1. So now there is not going to be any issues, and we are not having any new variables created here. Now similarly, we are going to delete everything here, and also all four of the methods, and also we are going to delete our fixed formatter class. So we are not going to need that. And what we are going to use is I searched from ChatGPT, and it gave me the solution. So the prompt I used was get hash code for a 3D bool array by converting it to a byte array and then to a string. So it didn't knew that we could create it this way. So get hash code graph, get hash code bool 3D. So as you can see, what it is doing, it is directly converting it to a byte array. So previously we were opening up this 3D array to 1D array, then we were converting it to long, and that long was converted to string by some different method which was using string formatter. So it was not pretty much that expensive, but there were more some memory issues. So what we are going to do is get hash code bool 3D for our graph. So that's it, and there are not going to be any more expensive functions. So here also, the only extra garbage collection is going to be for our byte array, and everything else is directly converted. So if we have done everything perfectly fine, we should be able to see our overall time decreased. So let's go inside our level generator and let's hit play and let's click simulate and let's pause and let's go inside our profiler and we are going to go in some of the expensive frames. So this is, yeah, so as you can see, overall our this is taking 83% and our grid set compare is only taking 0.1%, and get hash code bool 3D it is only taking 2.7%, which was needed, and everything else we cannot do there. So it is pretty much almost faster than before it was. So get internal hash code and most of the time is for this. So bit converter dot true string and string to get hash code both are not expensive, but array we used a byte array and we cannot save memory there, so we are going to do that. And as you can see it is 15% and overall timing would have decreased, so you are able to see that it is taking only 600 milliseconds to execute everything. Previously it took on like 900 milliseconds. And if we close our profiler and we are not going to need the profiler again, let's hit pause and let's check for the negative one. So we need to check if it is showing all of the solutions. So there are 327 solutions, and similarly we can increase the speed to 10,000 and our code will work perfectly fine. So this were the final bug fixes, and after that you should be able to find all of the solutions. So it will almost go till 180,000, and as you can see it is not traversing at a speed of 10,000. It is taking a little bit more time, but still it is pretty much fast. Previously we were going at the speed of 10 and after that we optimized and now we can have the speed of 10,000 and again it is going to take 1 second to execute per frame, and we are able to get all of our so as you can see everything is working perfectly fine now. The main issue with our current is let's decrease the speed to 1600 and let's set the speed to 0.01. So we are going to traverse check 100 of each, and as you can see that this is most of the unnecessary part. So there is already a 1 degree node here, so if we added some more conditions, then if it want to add a new node, then the only position it could add is the 1, 2 and 3 here. Every other position cannot have nodes, cause it won't ever get filled. So that's the issue, and it's not an issue. We just need to know like how it is going to work. And currently, as you can see, it is working pretty fast. We could run it for like 1.5 minutes, and it could give all of the solutions. And our current method is also not the best cause I told you we don't want to go and search for stupid solutions. And after we optimize a little bit, and the checking condition also needs to be fast, so we are not going to have the difficult checks or else the whole node condition like how do you call it, as we are just directly adding the node right now. So if we add some check condition, then it should also not be too much expensive, or there won't be any need for like adding that condition if it speeds up the time. Not speeds up, slows down our code. But if the branching factor is low enough, so how so suppose how do you call it as a branching factor? So let me show you. So as you can see, here, not here. So here, suppose it ended and this was empty. Now, currently, the only position that is going to be filled here, which is the forced move, if our current flow goes there, then the empty position check should return null. So there should not be any possibility for empty flows. And as you can see, the starting flow size was 1, 2, 3, 4, 5, and 6, and finally the ending flow size we returned it to 1. So the branching factor is going to help for most of the work. And again, if there are 1 degree nodes in the empty position, then it is not necessary to go through all the 2 degree or 3 degree nodes, cause eventually our 1 degree node should be get filled. And if we want them to get filled, then we will start at that 1 degree node first. And if there are any 0 degree nodes, that means the game is finished. Not the game, that node has no any prospects, and we'll delete that node. So we don't want to do that. It's neighboring, and empty positions are going to return null. And if there is a 0 degree node around our current position, then also it's going to be a force move, cause that 0 degree node needs to be filled. And we are going to see how we will do that. And that was it for this section. And in the next section, we are going to further optimize the code. And for now, we are storing all of our solutions inside. So yeah. So we are storing all of our solutions inside like 1 degree, not 1D, linked list. And what we are going to do is we'll store all of our solutions inside a graph next time. And whenever you want to show some solution, we are just going to open that graph. So let's end this section here and see you guys in the next video.